Good morning, students. So today we are going to take the class on quantum mechanics 2. So this is the continuation of quantum mechanics 1, and we are going to deal with unit 6. So this is about scattering theory, quantum scattering theory. So before starting the lesson, I would like to say a few things about today's auspicious day. So today we are going to celebrate National Doctors Day, so Physicians Day. So all physicians are very important. They are all saviors. So they are all life saviors of the rest of their lives. And of course, without doctors, we can't imagine. And doctors, usually all the physicians, they have lot of patience towards the patients to cure the disease. So we wish them all the best for their careers. So in fact, in medicine field, we know that the instruments, all the instruments, right from stethoscope to radiotherapy or scanning technologies, almost all the instruments, they are all based on physics principles. So we are so proud of saying that. So those instruments are based on physics principles. So without physics, we cannot have any instruments in medicine field. Especially scanning technologies and heart disease, people use quantum theory of scattering. So this is based on quantum theory of scattering, especially tomography. Tomography is a new technique. People learn about the stages of tumor. So what is the early stage, the beginning stage, or the middle stage, or even at the end of the stage? So we can find out only by means of scattering theory. So this is about tomography. So computer tomography, emission tomography, PET scans. So almost scanning technologies, people use quantum theory of scattering. So which we will see later. So in medicine field, nowadays the technologies are based on quantum field theory, quantum information, quantum scattering theory. So we are so proud that we are helping the medicine very well. Okay, so about quantum scattering theory, we have already learnt earlier. In quantum mechanics 1 itself, we learnt about the dual nature of light, dual nature of matter. So former was dealt by Albert Einstein. The later was proposed by de Broglie in the year 1923. So we know already. So this dual nature of light and dual nature of matter based on scattering theory. So without scattering theory, that phenomena would not have been obtained. Without that, the quantum mechanics would not have been evolved. So those theories are very important. So dual nature of light, we are talking about scattering theory. Without scattering, dual nature of light would not have been obtained. So out of scattering only, the structure of the atom has been found. Structure of the atom, the constituents of the atom. Of course, using alpha particle scattering, Rutherford scattering, people have found out the electron, proton, the nucleons, the constituents of the nucleons. Many nucleon particles like quarks, mesons. So everything was found out only by means of scattering theory. Without scattering theory, I 100% sure that there will be no quantum mechanics at all. So scattering theory is very, very important one. Even we can access the microscopic world or a nanophysical world only by means of scattering theory. So without scattering theory, we can't imagine quantum mechanics. So that's why it's given very important in quantum mechanics 2. So we are going to deal in quantum mechanics 2, we are going to deal scattering theory, and syllabus goes like this. So in the unit, we are going to discuss these topics. So we are going to discuss about scattering amplitude and cross sections. So today's portion will be, we are going to deal with cross sections, especially differential cross sections. We are going to deal with differential cross section or scattering amplitude. This can be dealt by means of theoretical work. this can be dealt by means of experimental work, and we are going to connect these two. So that's the idea. Okay, so cross sections, we are going to have a detector and we are going to observe the result, and this result exactly will be equivalent to the square of the scattering amplitude, which we are going to see now. Okay, so the relation between these two is very important 5-mark question, section B question. The relation between scattering amplitude and cross section is very important question. And of course the consecutive days, and we are going to deal with Born approximation and its validity, very important 10-mark questions. And the scattering by a screen coulomb potential, this also very important section B question, Yukawa potential. And another very important section C question, 10-mark question will be partial analysis, scattering length, effective range theory of S waves. Okay, L equal to 0, S waves, and optical theorem. So put together one question. Okay, and transformation from center of mass to laboratory frame will come under section B question. And of course scattering theory is a two-body problem. So scattering theory, we are talking about only two particles, so they will interact. So two-body problem. So two-body problem, surely we will be dealing with only the transformation from center of mass to laboratory frame. Okay, so that we are going to deal at the end of the class. Okay, so these are all the syllabus, the topics that we are going to cover under scattering theory. Okay, and today we are going to discuss scattering amplitude and cross sections. So first we will go with the introduction, which says about the historically the data regarding quantum phenomena was obtained from two main sources. Okay, firstly study of spectroscopic lines, secondly the analysis data from experimental results. So we can have the results from the experimental data and we can analyze. Okay, scattering theory is a valuable tool to study the structure of the atom, as I said earlier in the introduction. And the constituents of the matter, atom, nucleus, nucleons, quarks, mesons, all have been discovered only by means of scattering experiments. And especially Rutherford's discovery of nucleus, the discovery of subatomic particles such as quarks. So everything with the help of alpha particle scattering experiments, all those things. So they come under scattering experiments. And what we call this as, they come under what we call this as high energy physics. Scattering phenomena provide the standard tool to explore solid state systems, example neutron, electron, X-ray scattering, and so on. So in a scattering process, the collision between a beam of incident particles of definite momentum and energy. So this is the idea. So we have three parts. One is the beam of incident particles, another one is a target, another one is a detector. That's all. So that's all the ideas about the scattering theory. So we have beam of incident particles, second one will be target, and we are going to have a detector. So detector will be kept too far away. So beam of incident particles, they will impinge on the target and those particles will be scattered, and we are going to have a detector which are kept at the too far. So that's the idea. So three main parts are there in this scattering experiment. Okay, and of course all the incident particles will have definite momentum and energy. The scattered particles are detected by a suitable detector. So we have a detector. Detectors can be counters or cloud chamfers. So those counters and cloud chamfers will be kept too far away, so to detect the scattered particles. So that's the idea. A beam of incident particles, scattered material, so that will be a target material. Sometimes we call this as scattering center. Energy and angular momentum distribution will be measured by devices. The total number of collisions over the duration of the experiment is proportional to the total number of incident particles. We are going to deal with now. Okay, and the number of target particles per unit area in the path of the beam, what we call this is flux of a point. Flux, immediately we can think about flux means number of particles per unit area per unit time. So you have to remember. So flux means which is coming inside or which is going outside through a particular area per unit time. Okay, so whenever you think of incident particles or targeted or scattered particles, immediately we have to think only the flux, J flux. Okay, J means flux. Okay, J incident and J scattered. So there will be two flux points which you are going to remember. One is incident, another one is scattered. Okay, J incident and K J scattered. So energy, angular momentum distribution and the number of particles can be measured. So two types of scattering are there. One is direct scattering and another one is indirect scattering. So information about the target will be unknown. So in direct scattering, target will not be known. Those two things will be there. Okay, that is incident particles will be there, detector will be there. Target will not be known. Okay, so we know about the incident particle and the interaction of the scattering center. Indirect scattering, the information about the target will be known. So target is known. So we know about the incident particle and the angular distribution of the scattering particle, of course. Okay, so here target is known, here target is unknown. And for different applications, people will be using direct scattering and people will be using indirect scattering. It depends on the applications. Most of the applications are done only by this type. Okay, scattering, this type only. Especially in medical fields, as I said earlier, tomography to find out the stages of tumor, tomography, scanning techniques, computerized tomography, emission tomography, PET scan. So they are all used in using indirect scattering. Okay. Also, types of scattering, it's elastic scattering and inelastic scattering. Of course, we know the definition for elastic will be the kinetic energy of the incident particle will be equal to kinetic energy of the outgoing particle, scattered particle. So energy is conserved there. Energy is preserved in the first type. So there will be no loss of energy. Here there will be a loss of energy. Energy is not conserved. Energy is not preserved. So what we call this is inelastic scattering. Okay. Most of the time we will be using only elastic scattering. We will see. If the energy of the scattered particle remains unchanged, so kinetic energy remains unchanged before collision and after collision. So unchanged as the incident particle is known as elastic scattering. So as I said earlier, initial energy means kinetic energy. Talking about kinetic energy is equivalent to final energy. Hence the internal structure of the target remains unchanged. Very important one more question. Okay. The internal structure of the target remains unchanged in elastic scattering. Okay. If the energy of the scattered particle is different from the incident particle is known as inelastic scattering. So energy is not conserved, energy is not preserved. Okay, in the second type, the internal structure of the target is changed. Here it remains unchanged. Here it is changed. Here the mass of the particles may change. New particles may be created. Most of the collisions occur in nature are inelastic collisions. Okay, most of them. The energy will be always will be waste. It can be produced as heat. Okay, heat energy is produced. So something like that. And another very important thing will be your P equals P dash. So P is the initial momentum and P dash will be final momentum. So energy we said energy is equal. So momentum also will be equal. Okay. So if so, we know that P equals h bar k. We have already learned. Okay. In quantum mechanics 1, h bar k. So similarly there also we have h bar k prime. And if you equate to these two, then h bar will cancel. You have k equals k prime. So initial wave vector equals final wave vector. Okay, in this type, in elastic scattering. In inelastic scattering, this will not be equal. Okay. Another very important thing that about the scattering will be in scattering process, the energies will be always positive and continuous. Whereas in bound states, which we learned in quantum mechanics 1, for example, quantum well problem, finite quantum well or infinite quantum well, then linear harmonica, hydrogen atom. So all those things we learned only the energies are bound states. Energies will be discrete, whereas here energies will be continuous. They are all positive. Very important one more question again. In scattering process, the energies will be positive and unbound. It is continuous. Whereas in earlier, which we learned in earlier classes, quantum mechanics 1, some models as I said earlier. So they have energies will be negative values. So they are all bound values, discrete values. So you have to differentiate these two. So we are going to learn in due course two approaches, and of course we are going to learn only the first approach. We are not going to learn this one, and we are going to learn only this approach. So differential equation for the scattering of a wave by the observable setup, and thereby asymptotic solution is obtained. Asymptotic means the solution which we are going to get, which will be kept too far. See, for example, detector. So as I said earlier, three parts are very important for the any scattering experiment. One is the incident particle, then another will be target, and third one will be detector. Detector cannot be kept very close to the target. That's all. It will be burnt. So we have to keep the detector too far. Okay, because lot of heat will be produced during the collision. Okay, so at the time people will keep only the detector, which will be kept too far. So we have to assume that the R will be very large. Whenever R is very large, we have to think only the asymptotic solution. Okay, so asymptotic solution means R is very greater. So remember like that. Okay. So scattering is considered with the transition from, this is another approach, from an initial state to a final state. So there will be a transition between initial and final state of a different momentum and same energy to be observed. Now we are going to have some assumptions. One is we are going to discard the spin. So in this process we are going to discard the spin. So we are not going to take the spin into account. So spin of the particle we are not going to take. Okay. The incident and target materials or particles will never have spin. Okay. So we are going to consider. And second one is, of course, we are going to consider this elastic. Scattering is elastic. So no, there will be no change in internal structure of target material. And target will be very thin. Target should be very thin. Suppose if it is very thick, so what will happen? There will be a multiple reflection, multiple scattering will be there. Multiple scattering means we can't observe. So there will be, to avoid this one, so target will be very thin. Even in alpha particle bombardment, we will have to use only thin alpha particle. Okay, thin gold foil. So in alpha particle experiment, we will be using only thin gold foil, not thick gold foil. Okay, so to avoid multiple scattering. So interaction potential depends only on the relative position of the particles. Relative position means we will have to consider only two particles. As I said earlier, scattering problem itself is a two-body problem. So two body problems, there will be two particles, incident particles and scattered particles. So there will be two R's, R and R prime. Okay, R minus R prime. R is the distance between incident particle and R prime is the distance between scattered particles. Correct. So you have R and R prime. R minus R prime will give you relative distance. R minus R prime will give you relative distance. We are going to consider only again two body problem. Okay, we are going to consider two body problem. If there is two body problem, there will be relative distance. And of course we are going to change into one body problem, and we will see, we are going to assume that the mass of the particle will be mu instead of m. Okay, we will see later. So this is about scattering cross section. In a scattering experiment, one observes the collision between the beam of incident particle and the target material, as I said earlier. So beam of incident particles will collide on the target material. Okay, the total number of collision over the duration of the experiment is proportional to the total number of incident particle and the number of target per unit area. What we call this as flux of a point. The particles which interact with target get scattered with some angle. So the scattered particle will depend on the angles. One is the polar angle, another one is azimuthal angle. So we are going to consider only here spherical polar coordinates. So spherical polar coordinates, in which we have three coordinates, r, theta, phi. Correct? R, theta, phi. So these particles will depend all the three. However, r will be kept constant because we are going to have only spherical wavefronts. So scattered particles will have only spherical wavefronts, in which r will be kept constant, because in a sphere r is constant. So it depends mainly on theta and phi. Okay. After scattering, the particles which do not interact with the target continue their motion in the forward direction. I will show now, just now, after that, in 2 minutes time. Scattered in d omega. This is called d omega. Okay, solid angle. This is called a solid angle d omega. Along the direction, as I said, it depends on theta and phi, is as shown in figure 6.1. So this is the schematic diagram of a scattering. It is a scattering instrument. So this is a schematic diagram. We have the incident particles. This is a target material, and this will be a range of a potential. Okay, so this is the target material. So incident particles, target materials, and this will be a device. So only, as I said earlier, there are only three parts. We have only three parts: incident particles, target material, and that will be a detector. Look at the detector. Detector is kept too far. One, and second one is detector has a small device. It can be a counter, cloud chamber, as I said earlier. So it can be. So we have kept only the detector too far, which is very small area. So that's why we call this as differential cross section. It means a small area. It can detect only small number of scattered particles. Incident particles, which are coming from here, they will have wavefront, plain wavefront. They will have plain wavefront. So look at the wavefront. So they are all plain wavefronts. After scattering, this will go exactly like a spherical wavefront. Okay. So after scattering, we can get only spherical wavefronts. Incident particles will be plain wavefronts. Very, very important concept. So we are going to have incident particles as plain wavefronts, and scattered particles will be spherical wavefronts. So you have to differentiate these two. So now, as I said, this will be a target, and this is a target center. After the collision, the scattered particles will have spherical wavefronts. Okay. So it depends on theta and phi, and theta stands for polar angle, which is the angle between these two, your r and z axis. Okay, theta, and phi will be your azimuthal angle. So this depends on theta and phi, and d omega, as I said, this will be a solid angle. Multiplying these two will give you area, differential area, small area. So differential, and of course, very important thing is this will be observed by experimentally. So we can observe this one experimentally. So after the scattering, we can observe. Okay. So and of course, in addition to that, we have incident particles. Suppose if the particles, they don't scatter, so straight away they will go on towards in the z direction. What we call this as unpolarized particles. Okay. So they are all unpolarized particles. There will be unscattered particles. So there are unscattered particles, scattered particles. These scattered particles are detected by the detector, and detector area is very small. That's why we call this differential cross section. It is small area. Okay. So this is schematic diagram of any quantum scattering. Okay. Now number of particles scattering into elements of solid angle d omega is proportional to the quantity, which plays a major role in physics of scattering. So number of particles are very important. Number of incident particles are very important, which we are going to observe, and number of scattered particles also very important, which you are going to observe by the detector. So those two things are very important. One is flux of the incident particle, another one is flux of the scattered particles. Okay. J incident flux, J scattered flux. So you have to remember these two. So what we call this is differential cross section. So this is denoted by d sigma by d omega, and this sigma depends on theta and phi. Okay. So the expression for differential cross section is nothing but d sigma by d omega. So omega is solid angle. So suppose we are going to integrate, that will give you sigma. Sigma depends on theta comma phi. So total cross section. So this is differential cross section. Your total cross section is equal to n small n divided by capital N. Small n stands for incident particles, number of incident particles. Capital N stands for number of scattered particles. Okay. So the small n stands for number of incident particles actually. Oh, sorry. Number of scattered particles. This will be your number of incident particles. Okay. So this n divided by capital N. And the unit of this one will be number of scattered particles, solid angle per unit time. So it's given as unit time. So that will be 1 by T. And here it is given as per unit time per unit area. So this must be 1 by T multiplied by 1 by L square. So this one will get cancelled. You have only L square. Okay. Okay. So we have only L square. So The unit of differential cross section will be L square. Okay, L square. Very important one more question. The unit of differential cross section will be L square. Generally, the units can be in terms of Born. So 1 Born equals 10 power minus 24 centimeter square. 1 Born. So it can be milliborn. Sometimes people use milliborns also. So this is referred as 10 power minus 24 centimeter square. Look at the size of the atom. So this will be atom and nucleus. This will be around 10 power minus 10 to 10 power minus 12. Okay, 10 power minus 9 to 10 power minus 15. So this will be in that range. Squaring that will give you 10 power around 10 power minus 24. So that's why they have kept us 1 Born. 1 Born equals 10 power minus 24. So it is defined as the number of particles scattered into element of a solid angle d omega in the direction theta comma phi per unit time per incident flux. That is d sigma over d omega, which is equal to, which depends on 1 by j incident multiplied by dn by d omega. Dn stands for number of incident particles. Okay, number of incident particles. It depends both J incident as well dn. Okay, it's very important relation which will be using